So good afternoon, good morning, everyone, and welcome to this lecture. This is lecture number 3 in current electricity, and in the previous class we were dealing with current density. I hope you all remember current density. Current density, as you might recollect, it is a vector quantity, and the direction of this vector is same as the direction of current, and you can find out current density by dividing current with area. Do we remember this? Current is, as you can see, current is current density into area into cos theta. If you divide current by area, you will get the current density. If you multiply current density with area, you will get current. Do we all remember this? Everyone? Yes or no? We all remember this? Current and current density? Then we had the discussion where we were dealing with current and current density. This was a question that we were discussing in the last class, and I had given you time to think about it. I'll still give you time to get me the answer for this one. You have a copper wire whose length is 1 meter and radius is 1 millimeter, and then you have an iron wire of length 2 meter and radius of 3 mm. Current is passed through this wire. They are joined end to end in series. You have to find out the ratio of current density in copper and iron wire. What will be the ratio of current density in copper and iron wire? I will give you 2 minutes to solve this question. Let me know once you are done. I'll give you 2 minutes.
Option B, sir.
Option B. How did we get option B? Option B is the correct option. And how do we get this option? It is very simple to see. Let me just tell you. Current density. You can write simply current density J as current per unit area I divided by A. Now the current is same in both the wires because both the wires are in series. The same current will flow. So if the same current flows, I can say that current density will be inversely proportional to area. So what I can write, current density of copper divided by current density of iron will be equal to inverse ratio. So it will be area of iron divided by area of the copper wire. Everyone understands this? Yes or no? Now, area of the wire. Now, whenever we are talking about the wire, please remember this. The wire is something like this. It is in cylindrical shape. The shape is like a cylinder. This is a wire. Now, whenever we are talking about area of this wire, we are talking about this area. This area we are talking about. This area we are talking about for a wire. This area. Now, this area of the wire is nothing but a circle, and the area of this wire, cross-sectional area of this wire is the right term. The cross-sectional area of this wire is always equal to pi into r square. Do we understand this?
Yes, sir.
So cross-sectional area, whenever someone talks about area of a wire, it's always a cross-sectional area, and it is always equal to pi r square. So this will be equal to pi into radius of iron square divided by pi into radius of copper wire square, and you can see the iron radius is 3 mm. The radius of the copper wire is 1 mm. So this is 3 by 1 square. So you get the ratio as 9 by 1. The ratio of current densities would be 9 by 1, and therefore the correct option is 9:1. Everyone understands this? This is how this question has to be done. Or any question which comes on current density, this is how it has to be done. Everyone understands this?
Yes, sir.
Okay, that is great. I'll give you a minute to note it down. Everyone who has not understood this, I'm not getting communication from the other class. I hope you have understood this. Everyone, yes or no?
Yes, sir.
Okay, let us now move ahead and write some more definition. And remember, in this chapter, we have almost covered everything in the previous chapter on capacitance, the series parallel connection, the circuits, everything will come similar. Now, what is a slightly different is this current density and all these things. So there would be some terms coming in this chapter, and we must understand the terms that are coming in this chapter. So the first term, I mean, apart from current density, the first term that we are going to introduce in this chapter is known as the drift velocity or the drift speed. So let us now move on and write the next heading, drift velocity. Some people may also call it drift speed, drift velocity, drift velocity. What is this drift velocity? Now, remember, we are specifically talking about conductors here, and we are not talking about insulators here. Now, whenever there is a conductor, in this conductor, there are a large number of free electrons. In a conductor where there is a large number of free electrons, and these free electrons are moving randomly everywhere. The free electrons are moving randomly everywhere. So whenever a conductor is not connected to a battery or not connected to a voltage source, what happens? All these free electrons are moving randomly. All the free electrons of conductor are moving randomly, move randomly, and therefore there is no flow of net charge. There is no flow of net charge in a conductor which is isolated. What do I mean by this? If I say that this is a part of a conductor, this is a part of conductor, some electrons, some electrons would be moving in this direction, some electrons would be moving in this direction, some electrons would be moving in this direction, some electrons would be moving in this direction. They will be moving in all sorts of random directions. So if a conductor is not connected to a battery, this is conductor not connected to a battery, they will move in all possible random directions, and so the net flow of charge is zero. That implies the net current in the conductor would be zero, because if I take any section of the conductor, if n number of charges are flowing in this direction, n number of charges will be flowing in the opposite direction as well. So there is no net flow of charge, and hence if this is a conductor, a wire like this or a metal rod like this, not connected to a battery, there cannot be any current in this rod or the or rod or the conductor. Do we understand this? Do we understand this? Now,
Yes, sir.
Now what something happens when when these conductors are connected to a battery. Now, if I have a conductor connected to a battery, then what happens? If I have a conductor which is connected to a battery, and I will show you the diagram here. Now, this is the diagram of this conductor which is connected to a battery of voltage V, connected to a battery. Now, when this conductor is connected to a battery, what happens that because of this battery, there is a net electric field. Now, battery is put like this, and the electric field is from the positive terminal to the negative terminal. So, this is the direction of electric field. Now, whenever a conductor is connected to a battery, there is an electric field which is applied, and you can see the electric field which is applied is always going from the positive terminal towards the negative terminal, higher potential to the lower potential. Do we understand this? And that is also taken as the direction of current, the direction of positive charges. Positive charges flow from higher potential to lower potential. They flow in the direction of electric field. Do we understand this? Do we remember this?
Yes, sir.
Now, because of this electric field or the potential difference which is applied, what happens if you trace the path of any electron? It will be moving randomly, but it will be having a net velocity. It will be having a net velocity. It will be having a net velocity opposite to the direction of electric field. This is the green direction that I am showing. It will move randomly, but any electron, if you see if you see its net motion, it will have a velocity which is opposite to the velocity opposite to the direction of electric field. This velocity acquired by these electrons when electric field is applied or a battery is connected, this velocity is known as the drift velocity of electrons, and it is opposite to the direction of electric field or voltage. Do we understand this? Do we understand this? Have we understood this, bacha? No? We're not able to understand this? Do we understand this, beta? So we will write it. I'm not getting any response from yourself. When electric field is applied, electrons in the conductor move opposite to the direction of electric field with a constant velocity. This velocity, this velocity which is in this direction is known as the drift velocity. So drift velocity is the velocity acquired by these electrons when there is an electric field applied, and because of this drift velocity we have a current in the conductor, and this current is taken as the flow of positive charges. Therefore, the current in the conductor is opposite to the direction of this drift velocity. This is the concept of drift velocity. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note it down. Please note it down. Let me know once you are done. Well, I hope you have done this, and then we will move ahead and see the relation between different things that are going to come. So again, I will show you a diagram, the same diagram that we had just seen. I'm drawing it again, but now I am drawing it in this way so that we understand the relation between the different quantities that are coming. Now, what I have done is just change the polarity of the battery. So you can see the direction of electric field is like this, and this is the direction of current. Everyone understands this, yes or no? Which is the direction of flow of positive charges. Do we understand this, everyone? This
Yes,
is
sir.
the current flowing in the conductor. As you can see, the direction of electric field is like this, but you can see the drift velocity is like this. It's the opposite direction. You can see the length of the conductor is given as L, the voltage applied is V, and the electric field is E. The first relation that you must remember, here is this electric field E is potential difference divided by L. That is the first relation that you must remember from this diagram. Let me first write it, and then I will give you enough time to note it down. So first understand this electric field will be V by L. This is the first first what should I say? First formula that you must remember. Now there are other terms that are going to come here, and we will be noting down these terms that are coming on your screens now. The first term that you must understand is small n. This n is the number of electrons in a unit volume. In a volume of 1 meter cube, how much electrons are coming? Because electrons are the charge carriers. These are the electrons which are going to move with drift velocity, and because of this, current is going to flow. So n is the number of electrons per unit volume on the conductor, and this number will change from one conductor to the other conductor because it depends on the material of the conductor. A good conductor a good conductor will have more number of electrons that can move. A bad conductor will have less number of electrons. Copper is a very good conductor. It will have a large number of small n electrons per unit volume. A bad conductor like wood will have literally zero electrons. Do we understand this? Yes or no?
Yes, sir.
Okay. The other thing that we are going to see is the area of cross section of this conductor. As you can see, this is the area of cross section of the conductor. We have done a question on this area of cross section. This area of cross section is nothing but pi r square. More the area of cross section, if you have a very thick wire and a very thin wire, a very thick wire and very thin wire, obviously in the thick wire, suppose this is the thick wire, it will have more area of cross section, and therefore there will be more charge carriers, and therefore there will be more current. A thin wire will have less charge carriers, and therefore it will have less current. This V is the applied potential difference. I've already told you that. This E is the electric field. So these are the terms that you must these are the terms that you must remember. Everyone is there? Everyone is able to understand me?
Yes, sir.
I'm hearing voices that everyone is distracted. I hope everything is fine.
Yes, sir.
Okay, so the first relation that you must remember is E is equal to V by L. Now the second relation that you must remember is about the drift velocity Vd. Vd is given by current I divided by N into E into A. This is the formula for your drift velocity. This is the formula for your drift velocity. Now here, as you can see, one more extra term is coming, which is small e. So you can also note down the small e. Remember, capital E is the electric field. Small e is the charge of an electron, because electron are the charge carriers. So small e is the charge of an electron. This is the relation between drift velocity and current. You can write this relation in a different way. I will be equal to NAEVD. I can write this equation in the reverse order. NAEVD. Do we understand this, bacha?
Yes, sir.
Everyone understands this? So I can write this I I in this form. Everyone understands this? Yes or no?
Yes, sir.
Okay. Now, once you have the value of I, once you know the value of I, which is current, you can also find the value of J, which is current density. Current density is I divided by A. If it is I divided by A, I just divide this by I, N, E, V, T. N, E, V, D. That becomes your that becomes your current density. Current density becomes N E V D. Everyone understands this?
Yes, sir.
Current density, drift velocity, and the area of cross section E is equal to V by L. Okay? Everyone has noted this down?
Yes, sir.
Okay. This is the relation between current density, drift velocity, area, and the number of electrons per unit volume. Now, what all inference we can draw? What all inference you can draw from this results? As you can see from this result, we can find out that, and we'll write them as important notes. I'll just scroll down a bit. Important note number one: this drift velocity is, as you can see, directly proportional to current. Current is directly proportional to voltage difference. So you can write this drift velocity is directly proportional to the applied electric field. You will have to remember this relation. This is directly proportional to the electric field. Drift velocity is directly proportional to the electric field. Yes or no? At the same time, you can also see that this drift velocity is inversely proportional to the area. I hope we understand this. I hope we understand this. These are the two things that you have to remember about these equations? Everyone has noted this down? Yes or no? No, yes.
None, sir.
Everyone has noted this down? Okay. Now let me give you this question and let me ask you what is the answer. I hope everyone has noted this down. Let me give you this question and I await your answer. A wire has a non-uniform cross-sectional area as shown in the figure. Question number 1 this is. From A to B, the area is different. A steady current I, so the current that is flowing in the wire is constant I. A steady current I flows through it. Which of the following options is correct? Option A, drift speed of electron is constant. Option B, drift speed increases from A to B. Option C, drift speed decreases from A to B. And option C, the drift speed varies randomly. What would be the answer for this question? Drift velocity we are talking about, my dear friends. Drift velocity is what we are talking about. Can anyone tell me the answer for this one? What will happen with the drift velocity? Remember, current is constant. Current is constant. Current is constant. Anyone with an answer? Anyone with an answer? I've already also given you a hint. Anyone with an answer for this one? Anyone would like to try? There are 4 options. Which is the correct option? Okay. As you can see here, this current is constant. The number of electrons in a unit volume will be constant. Charge of an electron is definitely constant. So you can see, and we have also written that drift velocity is inversely proportional to the area. Drift velocity is inversely proportional to the area. That means if area is more, as you can see here, point B, the area is more, but at point A, the area is less. Where area is less, current density, drift velocity will be more. Where area is more, drift velocity would be less. So drift velocity at this point and drift velocity at this point will be different. Drift velocity at point A will be more. Drift velocity at point B would be less. And therefore, the correct option is option C, which is the drift speed decreases on moving from A to B. Drift speed decreases in moving from A to B because at point A, area is less. At point B, area is more. Do we understand this?
Yes, sir.
Were you not able to do it on your own, beta? Anyways, I hope you have understood this now.
Sir.
Everyone has noted this down?
Yes, sir.
Okay. We move to the next question. In a wire of circular cross section of radius r, electrons travel with a drift velocity v and a current I flows in the wire. So when the radius is r, drift velocity is v and the current is I. What is the current in another wire of half the radius, same material, and the drift velocity is 2v? So material is same, radius is half. What will be the current in the second wire? I'll give you 2 minutes to solve this problem. Option C and option C is correct. How do we get option C? Now, how do we get option C? So I know that formula. I can write it like this also. N A E V D. Now look at this option. The material is same. Now since material is same and the number of electrons depends on the material, therefore N is constant. N is constant. Then the charge of an electron, this will be constant. So now I can write current is directly proportional to A area multiplied by the drift velocity. So now I can write I2 current in the second wire divided by I1, the current in the first wire, will be A2 into drift velocity 2. I'm just writing it as V2 divided by A1 into V1. Now A2 area of the second wire, as you can see, the radius of the second wire is half. So if I want to write the area, it becomes pi into r by 2 square. Drift velocity is 2v divided by, for the first wire, the radius will be pi r square and the drift velocity is v. It is given in the diagram, it is given in the question, and from there I have taken these values. V and V will get cancelled, R and R will get cancelled, R square and R square will get cancelled, and what will you have is 1 4 will be in the denominator, 1 2 will be in the numerator, so you will get 1 by 2. So the ratio of I2 by I1 would be 1 by 2. If the current in the first wire is I, the current in the second wire would be I by 2, and therefore the correct option has to be option C, I by 2. All of us understand this? Yes or no? No, yes.
Yes, sir.
Good. Now these are the type of questions that are going to come in this from this chapter, which are slightly different from what we had done in the chapter on capacitance. Let me bring you one more question on this. The more the number of questions that you are going to do here, the better you are going to feel. And comes this question. I will call this question as question number 3. Question number 3 comes, and what is question number 3? A current flows in the wire of circular section with free electrons traveling with a drift velocity of v. So in the first wire, drift velocity is v. If an equal current flows in a wire of twice the radius, same currents, remember, what is the new drift velocity? Here current is same, so you just have to see what all things are same and you have to see what all things are different. Once you understand it, everything would turn out nicely. I will give you 1 minute to solve this question. So, option C is correct. Well done. How are we supposed to do this? Again, you just need to apply the same formula. I is equal to N A E V D and see what all things are same. The wire, the material is same, so N is same. The current, the charge of an electron is same. Equal current flows in the wire, so this is also same. So I can see V A into D will be a constant. A into D, you can write A into D. A into VD is nothing but a constant. That means you can write A1 into V1 is equal to A2 into V2, or you can write V2 will be V1, the first velocity, drift velocity, into A1 by A2. A1 by A2, the first velocity is given as V. Area of the first wire is pi r square, but the area of the second wire is twice the radius, so it becomes pi into 2r square. Be careful in taking the ratios. If you take the reverse ratio or you just make a mistake in taking square, you will end up with the wrong answer. Here the answer that you will get after cancelling out the common terms will be v by 4. Everyone understands this? Yes or no? I'll give you one more quick question and solve it so that this topic can be logged. Everyone understands this? This
Yes,
is
sir.
the next question. Question number 4, I am going to call it. Two wires A and B of the same material. So you must understand that both the wires are of the same material. Radius or radii, plural of radius, are in the ratio 1 is to 2. Current is in the ratio of 4 is to 1. You have to find out the ratio of drift speed of electrons in A and B. I'll give you a minute to get me the answer. Well done. The answer is option A. How are we going to do this? Again, I write the same formula N A E V D. So I V, it is not V into D, remember, it is VD, drift velocity. Now again we see they are of the same material, so N is same, E is same. So I can say current is proportional to A into VD. You have to find the ratio of current. So I1 by I2 will be equal to A1 into V1 upon A2 into V2. So I1 by I2 is given as 4 by 1. Radius are in the ratio 1 is to 2. So area will be in the ratio of 1 is to 4. And then the drift velocity is V1 by V2. So I can get from here V1 by V2 will be in the ratio of 16 is to 1. You should not make a simple mistake. If you just write something reverse, or if you multiply and divide wrongly, you have to multiply, you divide it, then you will get the wrong answer. So please be careful on that front. If you are careful on that front, these questions are not going to give you any trouble at all. Do we understand what we have done in today's class? We have understood the concept of drift velocity, and we have
Yes,
seen
sir.
how and what type of question come in this drift velocity. We will move ahead with the next topic, which is the Ohm's law, in the next class, and we will see what type of questions we are going to face in that particular topic. So again, I will request you to go through these questions. Remember this formula, write this formula as important formula, because you can have a question on this formula. because there are 45 questions and there could be one question, there would be one question from current, and it may be from this particular topic. So I'll see you in the next class tomorrow. Take care. God bless all of you. Bye bye.